Okay, so we don't got that much to cover left. So the best way to find the parameters to minimize the error to get the best line of fit is to use a technique which is called gradient descent. So what does gradient descent actually mean? So the outline of gradient descent is you given your cost function, given your smooth surface, your surface where you're representing your cost, the idea is to navigate through this terrain to finally arrive at the smallest point possible. So the idea is to start off at some initial point. You know, theta 0 and theta 1 could be any initial point that you want. Either it could be all zeros or ones, it doesn't matter. And then what you're going to do is you're going to keep changing these parameters iteratively until hopefully you get to where the minimum is supposed to be. So it's what's known as an iterative algorithm. You start at an initial step, and then you keep changing the parameters slowly and slowly until you get to the minimum. So you've probably seen this in first year. Probably this is the idea behind Newton's method, where you start at some initial root, and then you keep iterating until you finally find the root of that function. So it's very similar. Gradient descent is kind of like Newton's method, but it extends to n dimensions. Okay, so that's what gradient descent is about. So imagine that, you know, the surface is, you're like on some terrain, whether you're in a park, and then what you're doing is you're going to look 360 degrees and figure out, okay, where's the best direction I need to go down to a minimum. So you figure out, okay, so the direction's right there. You take one step forward, and then you look again, figure out where that minimum is, and then you keep stepping until you finally get to that minimum. All right, so let's see here. Okay. Oh, my bad. On the other page. So let's imagine you know, the cost function looks like below. So it kind of looks like this. It's convex, so it's not going to look like this. There's only one unique minimum, but for visualization, this is nice. So it kind of looks like this. This is not the cost function we're looking at, but it might, you know, I just wanted to show you this as an illustration. So it kind of looks like this, okay? So the idea is, you know, so start at an initial point. In this case, let's say we start somewhere over here, okay? So the next point is you're going to take a look 360 degrees and figure out which direction you need to go so that you're going downwards. You're going downwards to the minimum. Okay? So look 360 degrees and take a step where the minimum is. Yes. Okay? You want to find the point where you want to go down the hill. You want to go down the hill, and then you just repeat 1 and 2 until you hit the minimum. So that's the idea of gradient descent. Okay, so let's say you start here, and let's say, you know, the direction, the minimum's somewhere here, so you want to take a step in this direction. Okay, you're going to look 360 degrees, and you're going to keep stepping, keep stepping, keep stepping. You know, it's going to look like this. And then you finally head to this point, and then you stop. Okay, so that's the idea behind gradient descent, is you start at some point, and then you figure out which direction will make you go down and hit the minimum the fastest.
Question.
And that's what's going to happen, okay? Yes?
On a graph like that, couldn't you get trapped in a local minimum?
That's my next point. All right? And the linear regression function is convex, so there's only guaranteed one minimum. So that was my next point. Gradient descent is actually very sensitive to where you start. So if you have a function with local minima, then you will get a different minimum point depending on where you start. And that is the next point that I was going to talk about. So that's good. I'm glad you guys are being proactive. So let me just make a note of that. That was actually my next point. So gradient descent is very sensitive to where you start. Okay? If your function is not convex. So for example, let me do that again. Let me do this one more time. So let's say I started at an initial position that was maybe slightly to the right instead of where I initially started. So maybe I'll start over here, for example. In this case, what's going to happen is that it won't go down this way. It's actually going to go down this way, because what's going to happen is that it's trying to figure out a direction where a minimum would be best met. And it's going to go like that. Okay, so this is what would happen if your function was not convex. Okay, So with the linear regression cost function that I showed you earlier, there is only one unique minimum. So it doesn't matter where you start, you will always arrive at the same minimum. It may take longer to get there, but eventually you will get there. So that's the point of this cost function. There's only one minimum, so it doesn't matter where you start. So that's a very good point. Thank you for bringing that up. Okay, so, all right, let's see. So let's see, let me just write that in. So the linear regression cost function is convex. So it looks like a bowl-shaped curve. Okay, so this means that there's only one minimum. So this is both it's a global minimum, okay? So there's only one minimum. So it doesn't matter where you start. Okay? So for linear regression, you start off with a set of initial parameters, and the goal is to iteratively move these points so that the cost is minimal. Okay? So it might look like this. So on your contour plot, let me just pull this up. So visually with the contour plot, it might look like this. So maybe you start off with your initial point, let's say somewhere here, and then what gradient descent will do is that it will keep moving towards the minimum. So it looks something like this, and then you finally end up here, and that's what that parameter looks like. Okay, so start at an initial point. Doesn't matter where. So usually we just set it both to 0 and then keep moving towards the minimum. So on a contour plot, it might look like this. So this is your initial point here, and then what happens is every time you take a step, it'll move in the direct direction, until you actually hit the minimum. Okay. So that's all nice and good. So that's actually gradient descent conceptually, but what is the actual formulation? Like, how do you actually go ahead and compute the gradient descent? Well, that's not bad. So let me see here. So, oops, come on. Actually, I'm going to use the mouse. Okay, fantastic. So what's the actual algorithm? This is where it might get a little math heavy. Actually, it won't get that math heavy. We'll see that later. What's the actual algorithm? Okay. So first, you need to initialize theta 0 and theta 1. So usually it's 0, but you can set it to pretty much anything you want. It's sensitive, so depending on where you start, it may converge slowly or may converge faster. It depends. But we usually just set it to 0 when we don't really know the problem domain. And then finally, what you're going to do is you're going to repeat until convergence, the following. So you're going to update the parameter so that you move in the direction of the negative slope or the negative rate of change. Oopsie. See, so this is the main algorithm. Okay, so what this arrow means, this means to update, or what you need to do is we need to simultaneously update. And I'll talk about that in a little bit. So this is for j equals 0 and 1, right? Because there's only theta 0 and theta 1. So there's two parameters. Simultaneously update theta 0 and theta 1. So for each parameter, theta 0 and theta 1, you want to compute this equation. Okay, so there's a bunch of symbols. We probably want to cover that. So this symbol here is what's known as the learning rate. So this is the step size or the learning rate. And this is a strictly positive number, right? If you make the learning rate 0, that doesn't really make any sense. You're not moving anywhere, right? So you want to make this a strictly positive number. This number it varies, and the lab that I'll be assigning later on will explore how you change this learning rate to see how the algorithm converges. So this is the step size, or this is the learning rate, and this is basically telling you how much of a step you need to take in the right direction. So if the learning size is large, that means you're going to take a very large jump towards the right direction. If the learning rate is small, that means you're going to take a little baby step. So this controls how much of a step you're going to take in the direction towards the minimum. Okay? So how much of a step you're going to take. You take to the minimum. Okay? And then what this thing here is this is the partial derivative of the cost function, depending on what you're looking at. So partial derivative of. Okay, so notice that for theta 0, you take the partial derivative with respect to theta 0, and if it's theta 1, you take the partial derivative with respect to theta 1. So you compute this, and then you update your parameters. You keep iterating until it converges. So what I mean by simultaneously update is that you don't use any of the updated parameters to update the current iteration. So when you're updating the parameters for the current iteration, you only use the previous iteration's parameters. You don't use any of the updated parameters for the new version. Okay, so that's what simultaneously update means, is that you use only the previous parameters in order to update the next parameters. Okay, so simultaneously update. Let me move this up so you can see that equation there. So simultaneously, and I'll talk about why this is used, like what the actual intuition behind this is, and I'll talk about that soon. So simultaneously update, so this is use the previous iterations parameters to update the next iteration. Okay, so what I mean specifically is that something like this. So what you're going to do is you're going to assign the updates to temporary variables. So okay, so you're going to compute this for the first one. You're going to compute this for the second one. Sorry, I can't write. So this is alpha. Okay. And then the second one as well. Okay, so this is step one. So update in separate variables. Okay, and then finally, that's when you do the update in the end. Sorry, this is temp 0. Step number 2. Now update. Okay, so that's what we mean by simultaneously update. So when you compute the actual update, you store it in a separate variable, and then when you're done, you only use the previous iterations variables, and then you update when you're done. Okay, so you don't. So once you update theta 0, you don't use that update to update the theta 1. You only use the previous version's parameters. Okay, that's when we mean simultaneously update. You don't influence it based on the current iteration, only the previous one. All right. Okay, so let's dive into some intuition behind how this works. Like why would we want to use gradient descent for this? Why would it actually be nice to find the minimum using this? So what does the derivative term do? What is its purpose? Why is this so good to find the derivative? What does the derivative term do? Okay, so let's just stick with one variable now for now, so you can actually see this a little easier. So recall one variable cost function. So instead of 2, it's just 1. So you have theta 1x. So remember, the cost function looks something like this. Right, it looked like this, and then the minimum was over here. So this is theta 1. Okay, so let's say my initial point was somewhere over here. Okay, let's say my initial point was here. If you remember what the derivative does, the derivative measures the instantaneous change or the slope at one point. Okay, so if I wanted to find the derivative here, so let's say I wanted to compute my update. This was, this is theta 1, and then this is theta 1 minus. In this case, we're only dealing with one update. Sorry. Okay, if this is my initial point, this is what the update is going to be. Right? Come on. Okay, and then this measures the slope, right? This is the slope. So in this case, over here, this is a positive slope. Okay, and then this is a positive number. So if I decide to update this, right, theta 1 minus a positive number, what's going to happen is that the parameter decreases and moves to the left. So what's going to happen is that this now, we're going to move this way. This is what the update is going to give us. Okay? So what the negative slope does is that it moves in the opposite direction towards the minimum. So as you see, so this is your initial point, and what's going to happen is that it's going to keep moving, it's going to keep moving, and it's going to keep moving up until the point where it comes here. And then what's the derivative of this point? It's 0, right? So the slope will keep decreasing until it gets to that minimum. You reach that minimum when the slope becomes 0 or very small, and that's when you stop. Okay, so that's how gradient descent works. So you're given an initial point, and then that negative derivative makes you move in the direction of where the minimum is. And then you keep iterating until you get to that initial point. And it doesn't matter where you start, because I started here. Let's say I started on this side. Let's say I started over here, okay? You know that here is a negative slope, right? So if I decided to update, update my parameters again, this is, and then this here is a negative slope, right? So if this value is negative, right? And then when you subtract, you have theta 1, and then you have theta 1 plus a positive number, right? What will happen is that this will increase it. This will actually move it this way. Okay? It's going to move it over here now. So it doesn't matter where you start. The negative of that derivative will push you in the right direction towards the minimum. So if you're on the negative side, you have a negative slope, it'll push you in the positive direction. If you're on a positive side with a positive slope, it pushes you in the negative direction. So no matter where you start, it'll always make you point towards the minimum, which is why making this a convex function is so critical, because it doesn't matter where you start, it'll give you that minimum in the end. Okay? So that's why that is important. Okay, so I just wanted to cover that. All right, so you don't have to, I just wanted to give you a little bit of intuition. If that doesn't make sense, don't worry about it, but that's what I wanted to show you. Okay? So that's what I wanted to talk about. So the cost function is convex. Doesn't matter where we start, right? We get to the minimum. It'll probably take different amount of iterations to converge, but we get to the minimum regardless. So it doesn't matter where you start, you will get there eventually. Okay? So I talked about the derivative, but what about the learning? What about the step size? How does that play into account? How does that play in? So what about the learning rate? This one, setting this value, it's usually constant during the algorithm. So you decide on a set learning rate, and then you let that go for the duration of the algorithm. But depending on what value you choose, it may make the algorithm converge slowly, or it may make it diverge. So choosing the right alpha or choosing the right learning parameter is subject to experimentation. Okay, so what about the learning rate? So if the learning rate is too small, what will happen is that you're taking little baby steps at a time. So it's going to actually take you a little longer to get to the minimum. Okay, so algorithm may be slow to converge. All right. So in this case, it might look something like this. So this is your cost function like we talked about before, and this is the minimum over here. Let's say your initial point is here. So it might take you a long time to get to the actual minimum. So it may take a while. All right, so this is the first point. The other extreme is if you make the learning rate too large, like you set it to 1 million or something. In that case, what you're doing is you're basically jumping over the hill, and you're just going to keep jumping and jumping. You're never going to get to the minimum because your step is so large. Okay, so if alpha is large, algorithm can overshoot the minimum, can diverge. Okay, so it might look something like this, where you have, your thing like this, right? And then what might happen is that if you start here, if the step size is large, you may, shoot over this way, right? You may shoot over here, and then you might shoot back here, and then it's going to just go like this. So it's going to actually diverge because your step size is too large. Because if this is your initial point right over here, right, the derivative is fine. It points you towards that direction. But if your alpha is too large, you may overshoot and go over here. Right, so this might be the next one, and that's not good. It may actually overshoot, and you'll just keep bouncing and bouncing, and then the cost will become large, and it doesn't work. Okay? So the best thing that you can do, you'll take a look at this later, is to experiment and choose different learning rates and choose the one that gives you the lowest cost. Right, so this is subject to experimentation, and you'll find out in the lab. So, okay, so the learning rate is kept fixed during the algorithm. So some people may want to, maybe adapt the learning rate so that it gets larger or smaller when it gets towards the minimum, and you actually don't need to do that, because every time you take a step in the right direction, the derivative gets smaller and smaller. So the derivative is adapting, and you don't need to change the learning rate. You can keep that constant, but the derivative will keep changing as you go towards the minimum. So there's no need to change the learning rate at all. So you can just leave it fixed. Right? The learning rate is kept fixed during the algorithm, so there's no need to change. During the iterations, all right? So there's no need to do that. Kind of makes sense, right? Because, as we approach the minimum, the derivative term gets smaller, so it slows down anyway. Okay? So the update is smaller. Makes sense, right? So the derivative is smaller, the update is smaller. Because remember, you are updating by, so you're taking your parameter, you're subtracting by the negative derivative scaled by the learning rate. So if the derivative gets smaller, then the update is going to get smaller as well. Okay? So finally, so that's a nice intuition. So let's put everything together. So how can we use this algorithm to figure out the best parameters for to fit the line? Okay? So let's put everything together. So here we go. Gradient descent for linear regression. So this is the algorithm, okay? The first thing we need to do is you got to figure out how exactly we need to compute the update, okay? So if you recall, the cost function was this thingamajig right here, right? So it's theta 0, theta 1, and then you're summing over each training example. Squared, dividing by 1 over 2m, and you'll see why the 2 is good in a minute. And then the hypothesis was theta 0 plus theta 1. Okay? So the first step would be to initialize, right? So 1, initialize theta 0 and theta 1. And then 2, repeat until convergence. You want to repeat the following thing. So this is what the gradient descent was. Right, so you had theta j minus, and then, so remember that thing is a partial derivative. All right, so here, and then, okay? So now we got to figure what this term is. Okay, so let's go ahead and do that. All right, so this is for j is equal to 0 and 1. Okay. All right, so we got to define what this is. So how do we find the derivative term? How do we find this? How do we find this guy right here? Okay, well, let's do it slowly. Let's do it for the first one. So let's do it for theta 0. So I need to find the derivative of this with respect to theta 0. Okay, so this means that I have to differentiate this with respect to theta 0, and then my cost function was what? 1 over 2m, and then summation of 1 to m, and then this stuff, right? Okay, well, that's great. So I need to differentiate this with respect to theta 0. So what I'm going to do is I'm going to do a little bit of substitution. I'm going to expand it a little bit so you can see. If you recall, this guy here was our hypothesis. This is theta 0 plus theta 1. xi. Okay, so let me just write this out. So we have 1 over 2m. I don't need the sum anymore, so what I'm doing is this is theta 0, so I need the first training example, right? And then I need the second training example, right? And then I keep going all the way up to the last one, m, right? Oopsie. Come on. Okay. All right. So this is a summation of different terms. So the derivative has a linear property where you can just differentiate every single term in that sum and it equates to the derivative altogether. So what I need to do here is I got to differentiate every single one of these guys with respect to theta 0. So you got to remember the chain rule, right? So what you need to do here is you got to differentiate. So you got to take the power of 2, bring it down, and then you have to multiply it by this, and then you have to differentiate it with the multiplication there, right? So if you want to differentiate this, what do you have? So you have the 1 over 2m on the outside. Okay, so you have to bring this power down. So this is 2, right? Okay, and then this becomes to the power of 1, and then you have to differentiate the inside. It's the chain rule, right? So remember, I'm differentiating with respect to theta 0. So remember, every single variable that is not theta 0, you treat as a constant. So when you differentiate this, what happens? Well, theta 0 becomes 1, and then this becomes 0, right? And that becomes 0, right? Because you're differentiating with respect to theta 0, right? So this becomes 1. Okay, let's do the next one. Same thing. Right, this is a 2 here, and then this is 1, and then you just keep going. Okay, does that make sense? Like you have each of these terms, you want to differentiate them. So you bring the 2 down, you multiply by what's in here, and then you multiply with the derivative of what's in the inside. So theta 0 is what is left, and that's equal to 1. All right? So then you keep going, and then okay, and then this is 1. All right, so now, the reason why that 2 was good is because if you take a look, these 2's cancel out with this one here. That's the reason why you need the factor 2 there. It's because it'll cancel out nicely when you're trying to find the derivative. So if you take a look now, right, this derivative term is equal to, well, 1 over m, and then you're summing over each one of these instances. So summation from 1 to m of theta 0 plus theta 1 xi minus yi, and then you just multiply by 1, which is fine. And this is the update. So this is the update for the intercept term. Okay? Does that make sense? All right, so now we got to do it for the next one, and it's going to follow a very similar pattern. All right? So let me just copy this stuff, which is nice. Let me see here. So, let's see, let me just copy all this. Nice. Okay, so let me just, good, I don't have to keep rewriting stuff. So paste. Okay. Okay, so now I got to do with theta 1 now, all right? So theta 1. Oh, come on. Okay, this is theta 1 as well. Come on. Okay, theta 1 as well. Okay, so it's just substituting everything in again, but then I'm differentiating with respect to theta 1 instead. Oopsie. Okay, so now we're going to follow the same logic, all right? So let's see here. So you got, okay, so you have 1 over 2m, okay? And then if you take a look above, it's the same thing, so you have 2, and then this all stuff again. Okay? And now what's going to happen is you're differentiating with respect to theta 1. So all the other variables are constant. You don't treat them except for this one. Okay, so when you differentiate with theta 1, what do you get? You get x1, right? And then you keep going. So in this case, you got 2. Sorry, I messed up. This is plus. So this is 2. Okay, and this is x2. And then all the way down to 2. Okay, then again, all these 2's cancel, right? And then you're finally left with the following update. Equals, let's see here, j. Sorry, let me go back up. Oopsie, I forgot to put in the cost function. I have to differentiate with respect to a variable, right? I forgot to do that. This is, okay, my bad, sorry about that. So this equals 1 over m summation theta 0 plus theta 1 xi minus yi, and then this all multiplied by xi. Okay, so if you take a look, there's not that much difference. The only difference between the intercept term and the slope term is that you're missing that x of I value. So if you take a look, this is exactly the same as this guy here, but we have an additional term. Okay, so now the final update. So what you need to do is repeat convergence of the following. Okay, so all it is minus. So remember, this is alpha, right? You have this learning rate here. Okay? Right? And then finally, you have this guy here. I'm trying to make room so I can actually show you this in code. Okay. And there is our gradient descent algorithm with linear regression for one variable. Okay? So you start off at an initial point, and then you just keep computing this and updating until you converge the algorithm. Okay? It depends, depending on the problem, it might take a few iterations or it might take several thousand iterations. It depends. Okay. I'm going to end this with one small numerical example so you can see this in action, and then I'll actually show you how to do this in MATLAB code, and you can actually see the line of best fit. All right? So here's a quick example before I do the MATLAB code and we can end the talk. Example. Okay, so let's say we're given m equals 3 training examples. Okay, find theta 0 and theta 1 by gradient descent. Okay, we're going to assume that the initial, initial values are all 0. And I'm going to choose a learning rate of 0.1. Okay, so I have these parameters here. Not parameters, the points. 1, 2, 2, 4, and 3, 5. Okay, so so we're going to compute by gradient descent, and let's limit this to 3 iterations only. And also, let's compute the cost. Because to convince yourself that gradient descent is working at each iteration, you should see the cost going down. So that should give you a nice indication that it works. Okay, so the initial guess is theta are both 0. So the first iteration. Okay, let's compute the update, right? So theta 0 is what? It's theta 0 minus the, what is it, alpha, and then 1 over m to m, and then okay, so let's substitute stuff. So the initial was 0, right? So this is 0 minus the learning rate was 0.1, and then m was 3, and then we need to sum over this. So remember, these are all 0 initially. So in this case, you're just going to get the sum of all the negative y values. In this case, you get minus 2, minus 4, and minus 5. Okay, so the negative and negative becomes a positive. When you add up all this together, you get 2.5 over 3, which is 0.8333. Okay, and then when you want to calculate theta 1, you don't use 0.8333. You have to use the previous iteration, which is 0. Okay, that's what it means by simultaneously updating. All right, so now theta 1. And this is I equals 1 to m, and then the, right, I minus yi, right, and this is xi. All right, so let's compute this now. And this, so if this was 0 from before and forgot the learning rate, I'm sorry about that. So learning rate here, and then this is 0.1 and then 1 over 3, and this is all 0, of course, so again, you're just subtracting. So what's happening is you're adding up products, so in this case, you have minus y times x, so the minus y was 2, so you have minus 2 times the x value, which is 1, okay, and then plus, let's see, it was 4 and 2 and 3 and 5. 4 and 2 and 3 and 5. Okay. Okay, let me just double check if I got this right. Iteration 2. Yep. Good. And in this case, oh, sorry, I screwed up. This is, my bad. I copied the wrong parameter. The top is actually 1.1. Whoopsie. I copied another wrong parameter. This one is 2.5. So if you add this all up, you get 2.5 over 3, and this is 0.8333. Okay? All right. And then if you want to calculate what the cost is, okay, I'll let you do this yourself. I'm running out of time here. I want to show you some code. So this is okay, if you actually work this out, you get 1.5098. Okay? Let me just do the next iteration just to be complete, and then I'll just give you what the answer is for the last iteration. You can compute that yourself. Okay, so iteration 2. So what you need to do now is you have to do the update. So in this case, the previous value was 1.1 over 3, okay? And then you need the alpha, and then you have 1 over 3, and then you need to sum over all the values, right? So you have theta 0 plus theta 1 xi minus yi, okay? This here was 1.1 over 3. This here was 2.5 over 3, okay? So if you actually go ahead and compute that, right, so if you sum that all up, I'll just put the final answer in. This is actually 0.53, okay? We'll do the same thing. So theta 1, this is 2.5 over 3. 0.1, and then 1 over 3. Do this again. Minus yi. And then you have to multiply this by x of I. Okay, if you, so this is 1.1 over 3, and this is 2.5 over 3 again. All right, and if you do this, you get 1.2044. Okay? And then finally, if you want to compute the cost at this point, it looks like it's 0.3217. And then I'll let you do iteration 3 on your own. And I'll show you what the code looks like. So if you do this, the update would be 0.6027. And then this would be 1.3697. And the cost is 0.0861. So that's not bad. I wanted to do it a little fuller, but I'm running out of time, so. Okay. All right, so let me just end this by actually coding in a MATLAB for you so you can see for yourself. All right, so I want to write a function that's called linear regression. So it's going to take in a bunch of x points as an array. Y points the expected value, so alpha is the learning rate or the step size, and then the initial theta, it'll be a 2-column vector, and the total number of iterations. All right, so let's see here. I gotta see this a little better. All right, so what we need to do first is we need to figure out how many training examples there are. In this case, you can just set this as m, right? And then you want to figure out how many elements are in the array. So use a function called numl, and that calculates how many elements there are in the array. Okay, so let me just write a little function header. So finds parameters for linear regression by gradient descent. I'm going to post this code on the course website so you can download it and run it yourself. So x is a column vector of features, and then y is a the label for each value in x. Init theta is a 2-element column vector, and then n is the total number of iterations. Okay, so you first figure out how many training examples there are. Okay, and then what we want to do is this will return Oopsie. Damn. Yep. Yeah, of course. Let me see if I can do that. Let me see. Where are the options? Damn, I'm trying to figure out how to do it. I'm trying to figure whether I've never used 2015 before, so it's a little weird. Let's see. Compare, analyze preferences. Thank you, preferences. So code. Where's it? The editor. MATLAB editor. That's fine. Fonts. Ah, okay. Let's jump this to 16. Okay, how's that? Okay, fantastic. All right. So, so x is a column of, x is a column vector of features. Y is the label for each value in x. And if theta is a two-element vector, so it's the initial theta to use, or the initial parameters to use. I'm almost done. It's only going to take a couple 5 minutes. In this case, for example, you make this, and I also type pretty fast too. So, okay. So n is the total number of iterations, and then what is output? Output is theta, the final parameters, and costs, an array of costs for each iteration. Okay, so then what you're going to do now is you're going to initialize an array of costs. Okay, so this is a 0 vector of n elements. So what's going to happen is that each iteration will have a cost associated to each point. And then what we're going to do is we're going to plot the points in a graph. Okay, so what this is doing here is I'm making the points red crosses and making the size 16 pixels. Okay? And then what you want to do now is we're going to perform gradient descent. Okay, so what you're going to do is you're going to loop over each iteration from 1 up to n. And then what you're going to do, sorry, keep forgetting that this is not, I'm actually using an Apple keyboard. I thought it was a Windows keyboard, but it's okay. So for each iteration, what you're going to do is you're going to do the logic that we did before. So step number 1, compute the update. In this case, you have temp 0 equals, and then actually what I need to perform gradient descent. What I need to do here is initialize the output parameters to be the initial parameters for easier update. So you're going to do this. Okay. So then what's this? This allows easier updating. So for easier updating. So for easier updating. Okay. So then what you're going to do is you're going to compute what the update was. So you have theta. Remember, MATLAB starts indexing at 1. So you don't use 0, you use 1. And then what you're going to do is you'll do alpha divided by m. And then you have to sum this by what? You have to do theta 1 plus theta 2 times x minus y. And then that's it, right? So remember, this is alpha. So this is alpha, this is linear, so it's 1 over m. And then you have to sum over the hypothesis, which is this stuff here. So theta 1, theta 2 times x. And then subtract the training examples, right? And then you do the same thing. 2 minus sum. And then what's going to happen is the summation slightly changes. But what's going to happen is that you're going to take each of these points and multiply them by the corresponding x values, right? So that's how you do that. And now you do the update. Oopsie. This is temp 0. 1. I'm almost done. It's just going to take a couple more minutes. And then what I want to do here is I want to plot the line as we go. So what this does is that it creates an array of linearly spaced points from let's see here, the smallest value to the largest value for x. Okay, and then what we're going to do here is predict the, draw the line. Sorry, draw the line. So you do y equals. Okay, so what you're doing here is you're using the x points defined earlier, and we want to see what each y value is. okay? And then you predict those points, and then we can plot the line. So let's see here. Probably want to hold on. So let me just do hold on. Right, so this remembers all the changes you made. And then, let's see here. Okay, draw the line on the graph. And then, so what this will do here, this code here, what this does is that until we hit the last iteration, remove the line and update with the next line. And we'll pause it in between so you can actually see it update. Pause after each update. Okay, and then let me just put a title in. Actually, we'll leave it like that, that's fine. Okay, so let me see here. We'll save this now. Linear regression, that's fine. And then, so that's pretty much it. And then what I'll do is I'll run this code. So let me just define the points that we had before. So x was at 1, 2, 3. Y equals 2, 4, 5. Okay, and then I'll make the alpha 0.1 as we did before. I'll make the number of iterations 50, and then we'll run this. So x, y, and then, oh yeah, and theta. We'll just make it 0, 0 for now. Alpha, and then n. Ugh, crap. Let's see here. What did I do? What the hell? Theta 1, theta 2. Sorry, should work. No, it's fine. Index exceeds dimensions.
It's supposed to be theta 0 and theta 1.
No, it starts indexing at 1. So it should be fine. Let me just... Actually, oh, I didn't put... Okay, that's why. I flipped it. Woohoo. So alpha should be here. And then this is... I can't follow my own code. Oh, shoot. Sorry, let me just minimize this so you can see for yourself. Okay, so let me just... Busy. Oh, right. Let me just cancel this. Okay, so let me just do this again one more time. Yeah, so I'm going to fix this code later, but let me just run it again one more time so you can actually see it running. Okay, that's weird. Let me see. Pause, delete. Okay, that's fine. Okay, but anyway, yeah, I'll fix this code later, but yeah, that's what's supposed to happen. So it actually, it plots the line, and then you can see the line iteratively converging. So that's a little weird. Let me just close everything and we'll run it again one more time. Yeah, so that's what's supposed to happen. Okay, so you see the line starting, and then it starts to converge, 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 and then this is the line of best fit. Okay, so this code will be posted online for you to take a look at, and thanks for coming out.